Okay, and the sound is supposed to be coming from the browser?
No, it's from the speakers.
Oh, from the speaker.
And it
well, no,
came.
sorry. Oh, this is her, I see.
Yeah, there she is.
Actually, we just lost it all together.
We have reserve stories.
Frustrating.
No.
It's that also John to entertain to talk while I work on this.
We have meeting once a month. Open to the public.
How does meeting?
Not as a new room. New room, you know, most people like to go out to really large places.
Jessica, can you hear us at all?
Yeah, I can hear you now. Can you?
Oh, we don't know what we did, but it worked. Hurrah!
Usually how technology is.
Can you kind of see your audience, Jessica?
Yes, I can.
Oh, fantastic. I apologize for the late start. It worked beautifully before, but it's not working now. Well, it is working now, but it wasn't working a few minutes ago.
I could spin a basketball on my
John has been warming up the audience for you. He's been fantastic.
Thank you.
Oh, yes. And it took 3 librarians to get this going. Really fast, before Jessica gets started on her presentation, I know we're now running a few minutes late. My apologies. My name is Deirdre Tocoroso. I'm the services manager here. I'm also responsible for all of our science and technology programming here at the library for people of all ages. We are a NASA grant recipient, and we're very pleased that as part of that grant, we're able to host wonderful scientists like Jessica Sutter this evening. So again, we're very excited. Jessica Sutter is a PhD student at the University of Wyoming in Laramie, and she's joining us live this evening. So there she is. I'll let you get started, Jessica.
Hi, everyone. Thanks for coming. I'm going to do my best. It's a little tricky for me to hear you guys, so just if you do want to stop me at some point, please do yell really loud so I can make sure I can hear you. Like Deirdre said, my name's Jessica. I'm a graduate student in a...
Okay, we'll get going again. That was not good at all. I know. I hit the volume button and it went.
Too loud?
Oh my gosh. I'm not going to touch it again. Jessica, can you hear me?
Yes, I can.
No, she can't either.
Yeah, I can hear you.
Yeah, okay, I'm not touching anything again. I'm sorry.
Okay. Are we good? Sorry.
Yeah, maybe it is the cable. We're going to do this different next time. Yeah, thanks, John.
It's rrastro.org.
Let's see if this is any better.
Common member of the club will also have a club night once a month as well. And that's usually not doing anything before the club. little bit more involved than I'm showing up here.
It's back. I don't know if there's any sound though. That's the problem. Oh, there it is.
Can you hear me?
Can you hear us now?
Yes, I can.
Well, just go and see what happens.
Awesome. Thanks everyone again. Like Deirdre said, I'm Jessica, and I'm here in Laramie, Wyoming. It's a bit cold and windy. Not sure how things are doing on your guys' end. But I'm going to tell you a little bit about my research here looking at baby stars in nearby galaxies. Oops. So just to get started, I'm going to tell you a little bit about where I plan to go this evening. I'm going to tell you a little bit about who I am, and then we're going to kind of do a whirlwind tour of extragalactic astronomy and what researching extragalactic astronomy looks like. Then talk a little bit about why we might want to measure star formation, measure those baby stars I mentioned in my first slide, and then what I'm doing specifically, which is looking at carbon-2 emissions. So I'll talk about what that is. And then hopefully there should be some time for questions that we should be able to get going about my research or what it's like doing astronomy research or whatever else you have that you'd like to know more about. I'll be happy to answer. So I'm currently a graduate student at University of Wyoming. In 2015, I finished up a bachelor's in astrophysics at Whitman College in Walla Walla, Washington. And now I'm here in Wyoming. I just finished my master's portion of my degree in September, and now I'm going on to the PhD part. I'm also currently funded by the NASA Earth and Space Science Fellowship. So I'm doing this NASA at my library thing as kind of a fun little extra outreach program because I like talking to people who aren't necessarily in my graduate program at occasion. So I'm just spreading the word about astronomy, trying to get education out there as often as I can. So now we're going to get through that. We're going to talk a little bit about extragalactic astronomy, what that research looks like. And the way I like to start doing this is just to have you guys all just for a second, and sorry if you came to my earlier talk, this is going to be a little similar, but if you can close your eyes and picture the first thing that comes to your mind when you hear the word galaxy. So just the first image that whatever quintessentially is galaxy to you. When you've got that image, you can open your eyes. How many of you thought of something that looked kind of like this? Maybe a few of you. This is a galaxy. This would be 100% right. It's just a bunch of stars, about a couple hundred billion stars held together by gravity. This one has these nice spiral patterns. There's some pretty colors, blues, pinks, yellows, purples. And it's kind of like, this is kind of our image of what we think a galaxy looks like. How many of you thought of something that looks like this? This is also a galaxy. This is what astronomers like to call elliptical galaxies. It doesn't have that nice spiral pattern. It's missing those blues and purples. And the reason it's missing those blues and purples is because there are no young stars. Something happened to this galaxy that told it to stop forming stars at some point in time. Throughout universal history, something occurred and this no longer formed stars. So we're still a galaxy, still giant, still hundreds of billions of stars held together by gravity with gas and dust and dark matter, but this one doesn't have those young stars. It's no longer forming any new stars. So these we call spiral galaxies or blue and new galaxies. It has a lot of that blue light that comes from those young stars. And these we call elliptical galaxies or red and dead galaxies. They're only old stars. They're some of the biggest galaxies in the universe, but they have stopped forming stars. So one of the big questions extragalactic astronomers are trying to answer is what in a galaxy's history might make it stop forming stars? What determines if a galaxy is going to look like this or like this? And there's a few ways we can do it. One of the big ones that I think is really cool is we can use telescopes like time machines. We can do this. The speed of light isn't infinite. It takes time for light to travel between us and distant objects. So really close things, astronomically speaking, like the moon and the sun, it takes a few minutes or seconds for light to get between us. So when we look at the moon, we're seeing it as it was about 1.3 seconds ago because it takes 1.3 seconds for light to travel from the moon to the Earth. Sun's a bit further, so we're taking about 8 minutes-ish for light to get from the sun to the Earth. And what that means, what's kind of crazy, is if the sun went out, which it won't for a very long time, we wouldn't know for 8 minutes. It would take us 8 minutes to see that the sun had changed in some way. When we start talking about more distant things like other stars, we start getting to light year distances. So this is the distance it takes for light the distance light travels in 1 year. So the nearest star, Proxima Centauri, is about 4.3 light years away. So when we look at Proxima Centauri, we're seeing it as it was 4.3 years ago. And these are still stars within our own galaxy. When we start talking about looking at other galaxies, we're talking millions of years ago. So the nearest galaxy, the Andromeda galaxy, is about 2.5 million light years away. So anytime we look at this galaxy, we're seeing it as it was 2.5 million years ago. So we can start building up this picture of universal history by looking at more and more distant objects, getting slices not only in distance, but also in time. So the Andromeda galaxy, those nearby galaxies that we're seeing in the past few million years, that we call our local universe, those are our nearby galaxies that are approximately, we're seeing them at the same time as we currently are in universal history. But as we start looking further away, using telescopes, we can get this kind of idea of what's happening at other times within universal history. So with ground-based observatories, like New Mexico, a big one in New Mexico is APO, Apache Point Observatory, which I've gotten to use a little bit. It's really cool, and it's one of the observatories here on Earth that has allowed us to see galaxies that are about 6 billion light years away. So we're seeing them about halfway through the age of the universe. The universe is about 13 billion years old. So galaxies that are 6 billion light years away, we're seeing pretty much when the universe was middle-aged, I guess, or halfway to where we are today. When Hubble first launched and produced one of the deep fields, the Hubble Deep Field was produced in 1995, where Hubble just pointed to a blank piece of sky, or what looked blank to us, looked at that for about 100 hours, and got this image of all the galaxies that were in this little area in the sky that previously had looked blank. And we were able to see galaxies that were about 12 billion light years away, so pretty early on in the history of the universe. We can start seeing what galaxies looked like about 1 billion years after the Big Bang, after the universe started. And we can, again, kind of build this picture. How are galaxies changing between, right after that Big Bang, this 1.5 billion years after the Big Bang, to about 6 billion years after the Big Bang, to galaxies like Andromeda that we can see about now, so about 13 billion years after the Big Bang. We can start getting this picture, what's happening in galaxies, what might be causing this star formation turning off that we saw in those elliptical galaxies, or what might cause star formation to continue throughout universal history like you see in the spiral galaxies. And as we keep going, we keep getting better instruments. Hopefully in 2020, James Webb will launch, and we'll be able to see pretty early in the history of the universe some very early galaxies. Even without James Webb, though, we've been able to see pretty far back. This is an image of the Hubble Ultra Deep Field. So again, Hubble staring at an area of the sky, this little box here, that looked blank before Hubble had looked at it, looked empty, and just gets this beautiful image of all the galaxies that we can't see because they're so distant. And so pretty much every spot of light in this image is a galaxy. There's a few exceptions. This is probably a star. This is a star. This is a star. But everything else in this image is a galaxy. And what's really cool is each of these little green boxes pairs with one of these green boxes over here. And these are galaxies that are about 13 billion light years away. So almost at the beginning of the universe. These are some of the earliest galaxies we've seen, and we can get an idea of what galaxies look like just after they formed by looking at these galaxies. The most distant galaxy we've been able to image is this one pictured here. It's GNZ11. It's about 400 million years after the Big Bang. So this is what we're seeing, what it would look like, for what galaxies might look like 400 million years after the Big Bang. So it's about 13.3 billion light years away from us. The problem is that so far, we don't have a great image of it. It kind of just looks like a red blob. A little different to tell if it's a spiral or elliptical, what all is going on. So we have to take this light, astronomers have to take this red blob of light and figure out what's going on there, try to really understand what galaxies look like right after they formed, what they were doing, how quickly were they forming stars, what's going on from this small point of light, but it's really awesome that we can see things that are 13 billion light years away, which means we're seeing them as they were right after the Big Bang, which is crazy cool. The other thing I like to point out, so those are all the galaxies we've seen. This is an image some of you might have seen before of the cosmic microwave background taken with the Planck Observatory. So this is the most distant image we have of the universe. It's what the universe looked like. Approximately, it was about 400,000 years old. So galaxies haven't formed yet. This is pre-galaxy. Anything that's slightly red in this image, so like these clumps here, is an area in the universe that was slightly denser, slightly warmer than the rest of the universe. Eventually, if we could look at these images now, if light traveled, if we could look at these instantaneously, look at those clumps now, they would look like galaxy clusters, so large groups of galaxies. That's what these would eventually grow into. These bluer areas are areas where things were a little cooler, a little less dense. Those will eventually turn into voids. Just right now, it means there's not as much hydrogen gas, there's not as much dark matter in this area. There's a little bit more in these red areas. So this is the most distant thing we've seen, kind of the building blocks that will eventually become galaxies. So, like I said, with extragalactic astronomy, we're really trying to solve this history of the universe problem. How do we get from this kind of slightly denser areas and slightly less dense areas to these beautiful structures we see in the night sky, galaxies, galaxy clusters, giant voids where there just seems to be pretty much nothing? How do those things get built? How do we get to where we are? And what determines what shapes and structures we see in those? This is not actually, I should point out, this is not a real picture of a galaxy. I just wanted to include it because it's an artist rendition of what we think the Milky Way looks like based on our best estimations, based on kind of how stars are laid out. So this is what we think our own galaxy looks like to the best of our knowledge. I always like to make a joke, we don't have a selfie stick long enough yet to take a picture of the Milky Way, so we have to do some kind of estimations, but we're pretty sure there's a bar, and we have we've been able to pretty nicely track out where the arms are, how many arms there are, how they're moving based on the velocities of nearby stars, which we can get pretty accurately with a telescope called Gaia. But that would be whole other talk. That's not my research. I look at other galaxies, but Milky Way is really cool as well. So I thought I'd just stick that in there. Okay. And so to answer that question, how we get from clumps that are slightly more dense and slightly less dense to beautiful galaxies, one of the big ways we do that is through star formation, because galaxies are filled with stars. The structures we see in them are essentially just stars, clusters, stars within gas, stars within dust. Some of the big, you can clear out areas in galaxies with supernovas, so stars exploding. So in order for galaxies to grow and evolve, we need stars to form. And that's why I want to measure star formation, because measuring star formation is not only going to tell us what's going on with those galaxies that have had star formation turn off, but it's also going to tell us a lot about how galaxies are growing and changing at any point in universal history where we can measure that star formation. This image is also showing that as stars are forming, planets are forming. So if you're interested in how we could possibly get an Earth 2.0, it's really important to know how stars form. So again, not my research, but another cool thing about how different fields of astronomy are kind of related. So when we measure star formation, what we're essentially looking at are clouds of gas and dust, so a giant molecular cloud in a galaxy. If it gets to be a certain density, it can go through gravitational collapse, where we'll get little cloudlets and cores, so things that will eventually become stars dense enough that gravity's pulling them together really fast, and that'll turn into embedded star formation, and this is mostly what we're looking for. So it's when there are really young stars, these baby stars, but they're still surrounded by kind of their stellar nursery, the gas and dust that's going into forming the stars. So if there wasn't gas and dust there, we couldn't form the stars because there wouldn't be anything to form stars out of. But that's also kind of tricky because as kind of shown here, when there's a lot of gas and dust around these young stars, it can be difficult to see the light from them. So it can be difficult to measure how many young stars there are if they're still embedded in this gas and dust that was forming them. So we need to be able to correct for that before we, all the gas and dust gets used up, we form all the stars we can, and we end up with an older cluster. So what we do to measure this is we look for signs of hot, young blue stars. We correct for the fact that a lot of the light that's coming from those hot young blue stars is going to get absorbed or scattered by dust. So that's kind of like what I was talking about here. There's stuff in the way. We might not see all the light we want to see. That blue light that's coming a lot from those young stars is unfortunately really good at being absorbed by dust. So dust is just exactly the right size to absorb and scatter ultraviolet and blue light that comes off of young stars really well. So we want to look for other things that might indicate that star formation is going on to correct for that effect and still get total numbers of stars forming despite the fact a lot of this light that's coming from them is getting blocked. And then once we have those numbers, we can determine a total number of new stars that are forming in a galaxy or a star forming region or whatever else we're looking at. And just to kind of show that again, this is one of my favorites, so there's going to be another picture of this kind of zoomed in, but this is the Orion Nebula. So this is a star forming region within our own galaxy, so a stellar nursery within our own galaxy. All of the red light you're seeing is coming from hydrogen gas. So that's what's forming this. The stars are forming out of this hydrogen gas. We wouldn't have a star forming region if there wasn't hydrogen gas there. But it's also blocking a lot of the light from the young stars. There's a lot of young stars in here that would look really blue if it wasn't for all of that hydrogen gas. So we need to be able to correct for that effect. There's also some dust a lot of the times in these regions, so that's what's going on here. This is not a darker area of the sky. There probably still are stars in this area, but we can't see them because the dust is blocking the light from getting to us. So we need to be able to understand what's going on there. So in order to measure star formation, we need to see those young blue stars that we can tell are young because they're putting out a ton of UV light, a ton of blue light. We also need to know how to correct for the fact that there's stuff in these galaxies besides young stars. So there's dust, there's gas, and we have to be able to take that into account. And just again, like I said, this is the Orion Nebula because it's beautiful. One of the things I love about astronomy is how absolutely incredible everything looks in the night sky. The Orion Nebula is in the Orion constellation, which I believe is up in the southeast tonight, early in the night. So if you look at the belt, the three stars that are kind of together, and look slightly below that, that's going to be approximately where the Orion Nebula is, which is, like I said, stellar nursery in our own galaxy. So if you want to be able to point out some baby stars, there are a lot forming there fairly close to us, only a few thousand light years away. But again, what you can see is that this is messy. It's not just something that we can look at and count the young stars because there's a lot of other stuff going on in this nebula that's going to make that a little bit more tricky. So we need other ways of measuring young stars. And the ways we can do that are by looking at galaxies not only in optical light, like this one, so the light that we can see, but looking at other wavelengths of light. So specifically ultraviolet light, so light bluer, purpler than what we can observe as humans, and infrared light. So kind of like heat light, we're all putting, if you ever use infrared cameras, you're looking at heat essentially. Those will tell us a lot about what's going on in the redder than red, really longer wavelengths, lower energy. And so this is an image of one, or a pair of galaxies, I should say, in a few different wavelengths. We've got optical up here, so this is what we would see if we would look at it with our eyes. We got ultraviolet here from the GALEX telescope. Ultraviolet would be an awesome way of tracing young stars if it wasn't for that gas and dust. So one thing I think is really cool is if you look at this spot right here, there's probably star formation going on here. But in order to correct for that gas and dust, we also want to include some infrared light. Because as that dust heats up, because it's near these really young hot stars, it'll emit in the infrared. Specifically, we like to look at the 24 micron. So if we look at that same little clump in 24 microns, you can see it's super bright. There's definitely star formation going on here, but some of that light is getting blocked by dust, which is warming up and emitting in the infrared. So we can use that 24 micron to correct for the dust extinction, to correct for the dust absorption, and we can get a better estimate of how many young stars are actually in this little clump of young forming stars in the corner of this galaxy. So that's basically what we do. There's a few other things we can do. One other little trick is that we can use spectra. So if you've ever played with a prism, if you've seen a rainbow, that's essentially what spectra is. You're taking light and you're spreading it out as a function of wavelength. So you can see how bright a galaxy is, or a star cluster, or the sun, or whatever you're looking at. I like to look at galaxies. That's what I do. I'm a galaxy girl. So you can see how bright it is as a function of color, very specifically color or wavelength. And we can get a lot of information out of this. And this is so important because as an astronomer, almost all the data we have from space comes to us in the form of light. There's a few little places, if you're looking at lunar studies, if you're looking at some planets, you can get some rocks that will tell you a little bit more. But as far as galaxies, all we have is light. So we need to take that light and break it down as much as we can to really understand what's going on. And spectra are just an awesome way to do that. So we take our prism, essentially we put it on our telescope, and we're able to see how bright the galaxy is at each individual wavelength. And we can use these different wavelengths to measure different things. So this line right here, this really bright spike, is going to be a really bright spike in any galaxy that's forming stars because it's from hydrogen emission that gets excited when young hot stars bump into that hydrogen and cause this emission line. So this emission line is that red color that we saw back in the Orion Nebula, that pink color from, oops, sorry, one earlier. This pink color, this is all that hydrogen emission. So that one line right here is telling us a lot about how many stars are forming. So we can get a lot of information if we can get a spectra. Unfortunately, it's a little tricky just because if you spread things out by wavelength, it's going to be less bright than if you take just a big chunk of light. It's like putting those 3D glasses on. You need things to be brighter. You're blocking out some of the light, so you're not getting as much. So you have to be able to be careful with that. So spectra are great when we can get them. We can get a ton of information. We can do that. This emission, though, is still optical. It can still be blocked by gas and dust, so we still need to correct for that when we do that. So that's kind of my brief whirlwind tour of extragalactic astronomy. Now I'm going to talk a little bit about what I'm doing to try to help us build this picture of how galaxies grow and evolve by measuring star formation rates. So this is the Hubble Space Telescope, or not Hubble, excuse me, this is the Herschel Space Telescope. Unfortunately, it's no longer in operation, but when it was in operation, it measured infrared spectra of galaxies, both in the nearby and the distant universe. And the reason why we needed a space observatory to do this is because our atmosphere has a lot of water in it, and water is really good at blocking infrared light. So a lot of things that make it awesome for humans to exist on Earth make it really difficult for astronomers to see things in other galaxies. So we have to shoot telescopes up into space in order to actually really tell what's going on. It's one of the reasons why James Webb is actually going to look in the infrared as well. So Herschel looked in the infrared, and it got spectra of nearby galaxies for me and a lot of other people who are interested in infrared astronomy. And with those spectra, one of the things we could do is we could look at the emission from one very specific color, one very specific wavelength, the carbon-2 158 micron wavelength. So that's what I am looking at, this line right here, this really bright color. What you can see, this is kind of what we were looking at earlier, the optical emission. This is a lot brighter than even that. So this is often the brightest emission line in galaxies, and it's from singly ionized carbon. So carbon's what makes up a lot of us. There's also a lot of carbon in the universe because it's one of the first elements stars make. So stars produce light by fusing hydrogen into helium until they run out of hydrogen. Once they run out of hydrogen to fuse into helium, they start fusing helium into carbon, nitrogen, and oxygen because those are smaller elements still. So we get quite a bit of carbon in our universe from stars mostly. If that carbon is around young stars, they're putting out light that can ionize it. Photons hit the carbon, and one of the electrons go flying off, and we end up with singly ionized carbon. That carbon can then that ionized carbon can produce this 158 micron line. The great thing about the 158 micron line, sorry about that, is that it's so far in the infrared, the wavelength is so long, it can pass through dust and gas without being absorbed at all. So even though there's a lot more hydrogen gas in galaxies, the carbon-2 line is brighter than the hydrogen lines because it's at this really far infrared wavelength. So when we look at carbon-2, we don't have to worry about correcting for dust because it's not going to get blocked by dust at all. nothing in a galaxy is really going to block this light. So we see all of the carbon light that's coming from a star-forming region when we look at galaxies. So it's bright, we can see it really far away, and we don't have to correct for dust. So if we could use this as a tracer of star formation, it would be a really awesome way to get star formation rates where we don't have to worry about dust, we don't have to worry about anything else, and we can see it both in using Herschel, we can see it in the local universe, and using large millimeter arrays like ALMA, we can see it in the very distant universe. So we can get this really nice picture of how galaxies are changing as a function of time, what's going on with star formation as a function of time, without having to worry about dust corrections. And we do think carbon-2 should be tied to star formation, and that's because in order to get ionized carbon, first of all, you need high energy photons that are coming from young stars to actually ionize it. And then to get the carbon-2 158 micron line, you need things to bump into that ionized carbon, so it will emit this line. So I'm going to show that kind of another way here. So we have our gas and stuff in our gas and dust in our galaxy. We have young stars. Those young stars put out a lot of UV photons that are going to heat things up by photo-ejecting electrons. So they bump into dust grains, and they'll send an electron flying out into the gas, moving pretty fast. And as those electrons move around, they bump into other things, they cause things to heat up. And if those things, as they move around, as they bump into more things, if they bump into an ionized carbon molecule, they can cause the 158 micron emission. So the number of ultraviolet photons coming from these young stars, it should be directly proportional to how much carbon-2 emission we see. Because more of these means more heating of the gas, things are moving faster, more things are bumping into carbon, and we're getting more of this emission. So that's what we're hoping, is that we can really tie this carbon-2 emission that we can see really nicely to the number of young stars that are putting out those high energy ultraviolet and blue photons. And what we've found, and so in order to do that, not quite at the results yet. In order to do that, I'm looking at 28 galaxies, 30 regions and 28 galaxies that are all within about 10 million to 100 million light years away from us. This is all the local universe, we call it. They're essentially, even though the most distant one, we're seeing it as it was 100 million years ago, we're still saying it's about now as far as galaxy research goes. And we get these really nice images of those, of the nuclei of these galaxies, the center of these galaxies, as well as a few star-forming regions within these galaxies in carbon-2. So this is what that green circle, we're just going to zoom in on it. This is what it looks like in just the carbon-2 light. You can see it's fairly bright. And then I put down a circle, and I add up all of the carbon-2 emission from this circle, and I count how many baby stars there are using those ultraviolet and infrared ways of tracking numbers of new stars. We can see how well correlated they are. And what we found is that there is a pretty nice correlation. There does seem to be a good linear relationship with the number of stars formed per year per area. This is actually, so the units here are a little funky. I'm doing some math, so don't worry about what's going on, but this is essentially how many young stars there are. So more young stars would be up here, fewer would be down here, and how bright that light, that carbon-2 emission is on our x-axis, and what we can see is brighter carbon-2 means more young stars formed recently, which is great. We're still doing a few more tests, but we're hoping that this is something that we can do both in these galaxies in the nearby universe like we see here, and taking data from galaxies that are about 12 billion to 13 billion light years away, we can start getting an idea of how galaxies are forming stars at the very beginning of the universe. So that's kind of a brief look at what I do as an astronomer here at University of Wyoming. If you have questions, I will do my best to answer them. Also, I put my email and my website up here, so if you want to get in touch with me afterwards as well, this is a great way to do it. My website also has a little bit more information about my research and teaching, if that's something that interests you. Thank you.
Thank you, Jessica. Now, I know you can't
hear probably the best. So if someone has a question, I'm happy to shout it at the iPad, and then she can give us a good answer. Any questions? Yes, sir.
How long until we can get spectra of two tiny faraway galaxies to tell us your carbon-2?
How long can we get spectra of the teeny tiny far galaxies that will tell us a little bit more about carbon-2?
So the most, I think, pretty recently there was a paper that said they saw, they got spectra of a galaxy that was about 13-ish billion light years away, and they were able to measure the carbon-2 line even in that galaxy that was 13 billion light years away. So it's a really bright line, and with the millimeter arrays like ALMA, we can really start to get those very, very distant galaxies even, because it's such a bright line. It's still detectable.
Cool. Anybody else have any other questions? Or questions about Jessica? Yes, sir.
Is your research based on data from institutions, university, or analysis of existing databases?
Did you catch that, Jessica?
No, I'm sorry.
Yeah, okay. Is your research based on instrumentation from your university or analysis of data from other sources?
So all of my all the data I have is from the Kingfish program, which was done with the Herschel Space Observatory. So that was data that my advisor was part of the team that got it, but it's not technically through our university. It's not with our telescope. So University of Wyoming does have a 2.3 meter telescope, but since we're based on the ground, it's really hard to measure that infrared light from the ground. So the Herschel Space Telescope was what we used because we needed to get through the atmosphere without worrying about that. And the program that got the data had the one University of Wyoming collaborator, but also collaborators in England, and there's someone in Maryland. We're kind of all scattered around. So I think there's someone in Chile as well. You know this better, but there's about 30 of us working together to get this data.
Thank you, Jessica. Question from this side? Oh, yes, John.
I want Jessica to tell us how she got interested in astronomy.
John would like it if you tell everybody how you got interested in astronomy.
Yeah, so when I was growing up, when I was about 11, I think, I went to overnight camp through the local science museum. I lived in Portland, Oregon, so that was OMSI for me, the Oregon Museum of Science and Industry, which if you're ever in Portland, it's absolutely fantastic. And one of the nights we went to a nearby observatory and we got to look through a telescope, and they showed me Alberio, which is a binary star, so it's two stars rotating around each other. And what's really cool about Alberio is one of the stars is a yellow star and one of them's blue. So it's one of these few objects that when you look through a telescope, you can really see a difference in color. And I looked through that telescope and I thought it was the most beautiful thing I'd ever seen, and I knew that that was what I wanted to do, was look at things like this for as long as I could. And so kind of from there, I've just been going, plugging away, and I still like it, still excited about finding out what's happening in these galaxies and everything else.
Awesome. I always love that story, Jessica. Other questions or comments? Yes, ma'am.
Why is it important to study stars and galaxies billions of light years away? Is it something to do with our world?
Why is it important to study galaxies and stars billions of light years away? Does it have something to do with our world?
So I think it's a little tricky. It tells us the story of how we got here, I think is the big thing. Like why, when we look up at the sky, does it look the way it does? So maybe these aren't the most pertinent questions, but they're really interesting ones. It tells us a lot, not only about how we get to where we are, but also it can give us hints about where we might be going in the future. One thing we think is going to happen, let me just Nope, sorry. So one thing we think is going to happen in the next few billion years is that Andromeda is going to collide with us. And so we can actually, based on what we've seen, looking at other galaxies, looking at more and more distant galaxies, we can put together a picture of what we think that'll look like. So this is what the sky looks like now. And then this is kind of what they think is going to happen as Milky Way and Andromeda collide, and then eventually will become one galaxy, and it'll look something like this. Will turn into what we think will turn into one of those elliptical dead galaxies. So not only do we get a picture of how we got to where we are, but we can start putting together a picture of where we might be going as a galaxy, and how things might change within those as stars and everything move around. So just, I guess it's building up the history, building up our story, not just as a people and as a species, but also as a universe, which I think is really cool.
That's a really cool way of looking at it. Do you have any other questions? A couple. I think I said something else. You were here about a couple weeks ago. I remember. Do you have any questions for Jessica? No? Okay. John, any more questions? Oh, yes, ma'am.
I'm having a good time formulating my question. But it had to do with the carbon, and I know that we as humans have a lot of carbon in it. I think we're mostly carbon.
Yes.
And so to me, this was a very interesting information that and maybe she can tie that to your story that you want to know. Her question, because we are carbon, and the carbon is very involved in the story of star formation, and so that we are also part of the stars and part of that formation.
Yeah.
Stardust.
Definitely. I don't know if you caught some of that, Jessica, but an audience member made the observation that we are carbon, essentially. And she was fascinated by and was wondering if there was any way to tie together the fact that not only are we carbon, but everything else that basically that we're seeing out there that you're studying is carbon.
Yeah, and there's, especially in the past few years, there's been a lot of interesting research looking at where the different elements we see on Earth come from, what processes in the universe can make things like carbon, like oxygen, but also like heavier elements like gold, iron, all of those things. So the carbon that makes us up, that forms planets, mostly came from stars fusing carbon and then exploding and spewing it out into the universe. So we are here because a star formed, was hot enough that it was able to fuse helium into carbon and then exploded and put that out into the universe. LIGO, which is another really cool project that I always like to talk about, it's this gravitational wave observatory, was able to detect binary neutron stars merging together based on how those really dense kind of stellar corpses, how they warped the space-time fabric. So it was able to detect that. And what they were able to do from that one detection was they were able to figure out that events like that, so corpses of stars merging together, is where we get a huge portion of the gold we see in the universe. So if you have a gold ring or something, that probably exists because two dead stars merged together, which is crazy. As we put together this picture of how stars form and how stars die and how many stars might be forming, we get this kind of image of where the stuff that makes us up, every planet, every moon, every other star, where that came from, which is also really cool.
That is really amazing. I had no idea. Yes, ma'am.
He just wanted to say he likes your job.
Oh, you have a young audience member who was here a couple of weeks ago, and he wanted you to know that he likes your job.
Oh.
Yes, he's adorable. Yeah, you probably can't see him. He's kind of in the front corner, but you might recognize him if you did.
Astronomy is a lot of fun. Keep studying. keep reading. Thanks for coming.
So Jessica, do you have any idea right now where your research is going to take you over the next few decades?
It's a good question. I think so. Kind of. I definitely have a vision for the next few years. After that, it gets a little bit fuzzier. I know I'm talking with my advisor about putting in a proposal to get some of these really distant galaxy measurements so we can try to do similar things and build a continuous picture of how galaxies are forming stars over time without the need for dust correction. Most of other works that have done that have had to worry about dust corrections, and some of those might mean that they're multiplying their results by a factor of up to 30, which is a little iffy. So they're saying that we see this much light, so that would be 10 stars, but we think we're missing 30 times that light, so we're going to multiply by 30 to correct for that. So I think we could get this really cool picture of how the universe is evolving over time if we could get those really distant detections. So that's kind of my next step right now, and that would be the next few years, next 5 years or so, would be working with that. In about 2.5 years, I'm hoping to graduate, so get my PhD, and then I'm going to start looking for jobs where I could work and be not only doing research but also teaching. So that's something that I really love doing, is why I'm here, obviously. I really like teaching and working with people, getting others excited about the universe as well. So these kind of things are perfect for me. But I'd like to eventually end up somewhere where I can keep doing my research, keep looking at galaxies, trying to further our idea of how the universe has evolved and changed over the past 13 billion years, but also at the same time be working with students to help them spark their passions about astronomy.
Awesome. I think you're going to be a really awesome teacher. Out of curiosity, I know that NASA funds your research. What exactly do they do with it?
So one of NASA's goals is to build an idea of how the universe has evolved. So I think my research would be part of that. The grant I am currently on is just students working on different projects at different universities. We're going to get together this winter and share what we're doing. So just kind of building this knowledge base, building our understanding of the universe, and trying to get this complete picture, I think is my best. I've only been on this grant for a few months, so I'm still learning a little bit, but that's my understanding.
Well, congratulations again on the grant.
Thank you.
Quite a feather in your cap.
Yeah.
Yes, sir. You could come up a little bit. In fact, if you want to come up and actually ask your question into the iPad, I'm sorry, I couldn't hear that very well.
We have a young audience member that's coming up and he has a direct question for you.
Okay.
Would it be the two dead stars colliding that would come onto the Earth that would help start the Big Bang Theory?
This is about the two dead stars colliding. Could you repeat some?
The carbon coming onto the Earth, did that help start the Big Bang Theory?
The question is with the two dead stars colliding that brought carbon to the Earth, how did that help start? How did that relate in any way to the Big Bang Theory? Does it?
Oh, okay, that's a great question. So this would have all happened after the Big Bang. So the Big Bang produced some of the elements we see in our universe. Big Bang was the start of our universe, so everything at the very beginning, that 13.4 billion years ago, everything was really hot and dense and compact. And then it all kind of exploded out. And it starts to cool. We start to get things coalescing and forming stars, forming galaxies, all those other things. That's where that cosmic microwave background is. Before things are still so hot and dense that we can't form stars and galaxies. So the Big Bang, in the first few minutes, did form a lot of hydrogen and helium, a little bit of lithium, and a few other elements, but very, very light elements. It wasn't quite hot and dense enough to get carbon. So in order to get those heavier elements, we need the nuclear powerhouses that are stars. So hundreds of thousands of years after the Big Bang, things have cooled down enough that we can start forming stars. We can get gravitational collapse out of this cosmic soup that was the Big Bang that'll form stars. That those stars are going to be pretty much 100% hydrogen. But as those stars live, they create heavier elements. And eventually they die and spew those heavier elements out into the universe. And if you have two stars, so binary stars that are formed near each other and they die at similar times, and you get those dead stars, those stellar corpses, they can spiral around each other and they can produce the gold that we see. So there's all kinds of different processes that happen with stars, mostly involving giant explosions we call supernova, but also there's some other processes that can happen. Not all stars die in supernova. Our sun will not die in a supernova. But those processes, stellar life, and then stars dying and releasing what they created throughout their lives into the universe is how we get those heavy elements. So the Big Bang provides the stuff that can make the stars, and then the stars take that stuff and make it into heavier elements over time.
Thank you. Are there any additional questions? Yes, sir.
I think that the new technology of detecting gravity waves will assist her star study.
Will the new technology detecting gravity waves assist your study of stars?
So it gives us some I'm not sure it tells us a lot about how stars are forming, but it tells us some really interesting things about how general relativity works, so how space-time fabric exists. And so what it can tell us is that as light travels to us, it's traveling through the space-time fabric. So really understanding how bends in the space-time fabric might change the light we see could help us detect more distant objects. That's actually a really cool thing we can do, is we can use really heavy things kind of as lenses, because they put this big dip, essentially. They bend space-time fabric so much that light curves around them, and we can kind of use like really heavy objects like telescopes. So when I say really heavy, I'm talking galaxy clusters. So billions and billions of times the mass of our sun. So lots of suns, lots of dark matter. So understanding how that works might help us measure really distant objects, really distant galaxies, and get better measurements of what's going on there, get the light enhanced by gravity warping the light and pushing more of it towards us. So that could help us. The measurements of what the binary neutron star merger, that tells us more about what's going on in the end of stellar life. So that's not so much what I'm interested in, but it's still really cool. It's also amazing. The really cool thing about LIGO is that Einstein predicted these gravity waves about 100 years before we were first able to measure them. So it really tells us that Einstein got a lot right when he explained how space-time works. And so we can use that to better understand what the light is traveling through to get to us.
That's really cool. Anybody else have any? Oh, yes, John.
Is there any benefit of looking at quasars in your work? Because quasars are some of the earliest things from our universe, right? And they're very incredibly bright. So we can see even with a backyard telescope, we can see a quasar that's billions of light years away. Is there any benefit for your work of studying quasars?
Were you able to get most of that?
I heard the word quasar.
Is there any benefit to your work in studying quasars?
Oh, so quasars are great for looking at things that are really far away because they're so bright. One of the things I need to check is that my way of measuring star formation is going to work in quasars. So we're not quite sure about that yet, because since quasars are mostly fueled by accretion onto supermassive black holes in the center of galaxies, we're a little concerned that that might change the ionization states of carbon in these galaxies, and we might get emission in carbon that isn't related to star formation. So I do need to check and make sure that the quasars will still follow similar patterns. So it's something I'm planning on doing. Preliminary work has found that it doesn't seem to be an issue, but I'm still testing that out a little bit. So they're awesome because we can see them so far away because they're so bright, but the carbon-2 light is not what we're looking at when we talk about how bright quasars are. They're similar to normal star galaxies in terms of brightness, so it's not going to affect, they don't affect my work a lot, but they're great tools for getting an idea of measuring these really distant objects, these earliest objects. So they tell us a lot about cosmology and the structures of the universe, but not necessarily when I'm doing the star formation.
Cool. Thank you, Jessica.
Yeah, of course.
Any other questions or comments for Jessica on her work? Fantastic, Jessica. Thank you so much. I don't think we have any more questions this evening. Do you have anything else for us?
Nope. Thank you guys for coming. I love talking about this. It's always a little, I'm still getting used to this virtual stuff, so this is a lot of fun for me. But do seriously feel free to email me if you have any, if you think of any other questions, or you just want to get to know more what it's like to be an astronomer. I am always happy to answer emails.
Fantastic. Thank you so much. I will share your email address. Oh, we do have a question. Yes, sir.
Oh.
How about the black hole? The black hole.
The black hole. And
I just want to know when.
okay. Somebody would like to know if you have anything to say about black holes.
Yeah.
Well, with galaxies, the thing that's really cool is every galaxy has a supermassive black hole in the center of it. So astronomers have measured a few types of black holes. We have kind of two categories. We have ones that are similar in mass to our sun, and then there are supermassive black holes, which are millions of times as massive as our sun. So the one in the center of our galaxy we call Sagittarius A, and it's just this incredibly massive thing that is at the center of our galaxy, and there seems to be one at the center of every galaxy, and we're not quite sure how they form, which is kind of crazy. It's kind of a weird mystery that we're trying to solve, but they're in every galaxy. The solar mass black holes we see are mostly from the remnants of really, really big stars that eventually collapse, and what's left over afterwards is this super dense thing that we don't really know what it is, but came from a very large star that eventually ran out of fuel and fell in on itself. They're pretty cool objects, but I kind of study the opposite side. Like I said, I look at stellar birth, and that's more on the stellar death.
Thank you. Do you have time for one more question?
Yeah.
Perfect. Yes, sir. Is it the black hole at the center of every galaxy that keeps the galaxy in orbit?
So not quite, it's not quite massive enough to hold everything together. We have been able to measure stars rotating around the center of the black hole, around the black hole in the center of our galaxy, sorry. So it's definitely holding those ones in place, but we're far enough away. We're about, oh gosh, let me make sure I get this right. About 30,000 light years-ish from the center of our galaxy. So it's not really holding us in place. That actually gets to another crazy topic, which is dark matter. So it's the dark matter that makes up most of the mass in our galaxy, which is matter that we can't see, but is definitely there. So it has mass, but it doesn't interact with light, so we can't observe it. And that's kind of what holds the galaxy together. So not so much the black hole at the center of the galaxy, but this dark matter that's surrounding the galaxy, not just in the center, but all around it, all over the place. So that's a whole nother topic.
That's super cool. I would love to see a presentation on that, actually, personally. I think we're all done with questions right now. Jessica, I will, in case people can't quite see your email on the screen, I will happily share your email with anyone that has additional questions.
Great.
Thank you again so much for appearing here with us tonight virtually. I apologize that it took us a little bit to get the technology up and going. I'm hoping to talk with you soon. You'll probably see an email from me. So thank you. Again, thanks, Jessica. I'm going to go ahead and take you off right now. We really appreciate this.
Thanks for having me.
Thanks. Oh. Everyone else, really fast. Oh, she is still there. She didn't leave. There. If anyone is here that would like to really consider to fill out a survey for our NASA grant, these surveys help us. So they only take a second. You don't have to